Hi, it's Miss Martin. I'm going to take you through a lesson today on a new topic that we've not covered yet, which is energy changes. So this is going to take us up until the end of the year now. It's only going to be 2 lessons for most of you, and it'll mean that you've finished all of the paper 1 content for chemistry before the summer. So what I'd like you to do is I'd like you to use the skills that you already have, which you've developed through the last year, to be able to describe the trends which you can see in the graph, which is on the right hand side of the page. So this is in the booklet. If you are in top set, you need to be using the higher booklet. If you are in set 2 or set 3, you need to be completing the foundation booklet. So you can answer this either in the blank space, which is left for you in the booklet, or you can just do it on a piece of paper, okay? So I've given you some pointers about how to do this. So you've got 3 categories, so 3 different conditions. There's large lumps of lime, which is just limestone, small lumps or powdered, and you're measuring the temperature of each one when they're added to water. So as time increases, what happens to the temperature for each of the sizes of the lumps? For example, if we do large together, the temperature has increased. For example, at 0 minutes, it is 18 degrees Celsius, whereas at 5 minutes, it is 33 degrees Celsius. So use the sentence starters to give me a description of what this data is showing us. I'll give you 3 minutes to do that. So what I recommend you do, just pause the video and then resume it when you're ready to go. And I'm just going to go through the mark scheme now. So like I said, pause it until you finish the task and then resume it when you are ready. So like we said, after 5 minutes, the temperature's increased for all sizes of lime pieces, okay? The pattern is that the smaller the pieces, so from large to powdered, the higher the temperature rise. And remember, when we're describing, we always give specific figures from the data. So I've said, for example, the powdered lime gave a rise of 100 degrees Celsius after 5 minutes, whereas the large lumps in comparison gave 33 degrees Celsius. Apologies for the error I've made there. I've said calcium oxide for some reason, which isn't right. So correct your answer, and if you didn't know how to do a describe question, just your success criteria is talk about your general patterns, like I have in the first bullet point, and then you use your specific figures from the data to back it up. So let's move on. What I want us to be able to do by the end of this lesson, some of you who've been part of the live lessons will already be confident with this, but I would use this as revision. We all need to be able to define endothermic and exothermic reactions and give examples of each type of reaction. We're going to give some everyday uses of those 2 reactions. We'll start to evaluate them, and we're also going to understand what it looks like on something called a reaction profile graph. So have a pen and paper handy, because we are going to be doing some sketching of graphs, and obviously it's very difficult to do that on a computer unless you're really good with them, which personally I know I'm not. So starting off with an exothermic reaction, there's a space in your booklet where you can write this information down. If you prefer to write your own notes by hand, please do that. So exothermic reactions, they release thermal energy into the surroundings. So in an exothermic reaction, what you can expect is it will cause a temperature increase. So exothermic, the temperature increases because thermal energy is being released into the surroundings. So what are some examples? You can write this in your booklet as well, the space. Combustion, which is burning. Respiration is also an example of an exothermic reaction. neutralisation of acids with alkalis, which we covered before we ended up having to work from home, and also the reaction of metals with acids. Okay, so anytime that you've reacted magnesium with acid, what you would have been able to feel is that the test tube got warmer, and that's because it's an exothermic reaction and it is releasing thermal energy into the surroundings. So make sure you make a note of this in the correct space in the booklet, or you've just written it down in your own notes. So a couple of examples of exothermic reactions. You've got hand warmers, and in terms of obviously being able to evaluate the uses of those, you just need to discuss the fact that yes, it does give off heat, but actually these chemical reactions aren't reversible, so obviously it's not very economical. But it's quite rare that questions like that come up, so please don't worry too much about that, as long as you can state a specific example of an exothermic reaction. So in the booklet you should have written down your definition of an exothermic reaction, and you should have given 2 examples as well. And I'm going to move on to talking about endothermic reactions, and there's a space in the booklet as well where you can make notes on this. So these absorb heat energy from the surroundings, so it's kind of the opposite to what an exothermic reaction is. So if heat energy is being taken in from the surroundings, what you will notice with an endothermic reaction is that there will be a temperature decrease. So another example of an endothermic reaction is thermal decomposition, because basically you always have to put energy into an endothermic reaction. So if we heat something, like we do with thermal decomposition, heat energy is being taken in from the surroundings, so it counts as an endothermic reaction. So taken in is an endothermic reaction. So your key to that is remembering it's a decrease in temperature. So what are some examples? The common ones that we talk about, for example, thermal decomposition. So breaking down of calcium carbonate, for example. Photosynthesis, because you're taking in heat energy, light energy from the sun. So please make sure that you've written down those common examples in the space in the booklet. And you should know that even if you don't get those examples, if you do get an application of that, you should be able to recognise that actually it is an endo or an exothermic reaction based on whether the temperature increases or decreases. So an everyday application of this would be a ice pack, which is basically the opposite of an exothermic reaction. So this is where it gets a little bit more difficult, because once you understand the definitions for each one, and you understand that an exothermic reaction gives out energy to the surroundings, and an endothermic reaction is opposite, it takes in thermal energy from the surroundings. You can show that using something called a reaction profile, which looks like this. So I've labelled the reactions, reactants and the products for you, and the definitions are also given to you. So the reactants you should know is what goes in, and the products are what comes out. So I'm only going to focus on the exothermic reaction profile to start off with, which is on the left. So what you should notice is that basically these graphs are made up of 2 straight lines, and they're joined up by a hump in the middle. So on my exothermic reaction graph, what I should notice is that the line for the reactants is always higher up than the line for the products. So please make sure that you filled in the section of the booklet that asks you what a reactant and a product is. And I've put 2 examples of chemical reactions at the bottom, and I've highlighted in different colours what the reactants and the products are to help you out. So in an exothermic reaction, like I said, the line for the reactants will always be higher up than the products. So if you think about it like a normal graph with axes with figures on it, basically the reactants have a higher value, so they have a higher number, a higher energy than the products. So the products must have lost energy somewhere. Where have they lost the energy to, based on our definition of what an exothermic reaction is? So you can write that down in the space in the booklet. So I'm going to give it 30 seconds thinking time. Pause the video if you need longer. So the line for the products is lower down, so it's at a lower potential energy because the energy has been lost to the surroundings. If we now move the focus onto the graph which is on the right hand side, the reactants you may notice are now lower down. It's at a lower potential energy than the products. So the products must have gained energy, but where have they gained energy from? Just take 10 seconds to think about that and to finish the sentence in your booklet. Pause the video if you need longer than that time. So the reactants are lower down than the products. The products have gained energy, and that is because they've taken in energy from the surroundings. Make sure you're using these specific keywords, so surroundings, taken in, given out. You're always talking about energy. That's what my axes are labelled with, and they're labelled with that for a reason. So if you always just focus on those 2 definitions, so that an exothermic reaction gives out energy to the surroundings, so it loses energy effectively. So the products are going to have less energy. That's why the line is lower down. If you flip that around, an endothermic reaction takes in energy from the surroundings. That's why the line for the products is higher up. Just remember, it's just 2 straight lines and you join it up with a hump in the middle. And I'm going to talk about what that represents now. So now we can describe and explain why the graphs look like that. We need 2 more components, and we need to be able to explain what those components represent. So I'm going to start with looking at the red arrow. And the red arrow represents something called activation energy. So the activation energy, really simply, is just the minimum amount of energy needed for a reaction to take place. So without that amount of energy being achieved, you wouldn't get any products out effectively. So you can label that on a reaction profile by sketching a very faint line, straight line, along from reactants, just like I have in orange. And you also do the same, you sketch a nice neat line at the top of the hump, just like I have. So along the line for reactants, just carry it on along using a ruler, and along the top of the hump. So all you need to do, just like I have in red, is just add an arrow between those 2 lines, and that'll give you your activation energy. Make sure you've got your definition for activation energy down in the booklet. And then the last thing we're going to look at is the green arrow. And what the green arrow shows you is the overall energy change. So basically, how much energy has been gained or lost during this reaction. And you can summarise that. It's the difference between the energy of the reactants and the products. and you label that. You can use the same straight line from the reactants, and you do the same thing along the line for products, and it's just the gap in between, just like with the green arrow that I've drawn. So make sure that you've got the definition down in your booklet, and you've drawn the arrows on in the booklet just like I have on the diagram here. It's really simple to do that. If you just go onto the insert bar on Microsoft Word and then you click on shapes, you can pick a double-sided arrow out of there. But if you do really struggle, what I'd do is just get a piece of plain or lined paper and then just sketch one out for yourself. Just to summarise, we've gone through the definition of each reaction. We've described how you can identify each reaction, and we've drawn reaction profiles as well. So to summarise, what I would like you to do, this is the question that I gave you for the do now task. I'd like you to tell me, is that showing me an endothermic or an exothermic reaction? And you need to explain why. What I'd also like you to do is I'd like you to draw a reaction profile for this reaction based on what your answer for part 1 is. So just pause the video for as long as you need to answer those 2 questions. So you should have said that it's an exothermic reaction. How do you know that? You know that because the temperature is increased for each one. Because the temperature is increased, you know that energy is being given out to the surroundings. So your reaction profile graph, if I just draw one, very roughly here, emphasis on very roughly. So I have my line for my reactants, and then I know that the products will be lower down because energy has been lost to the surroundings. Then, like I said, all you need to do is join it up with a hump like that. And if I was to label my activation energy, if I wanted to stretch myself, obviously you'd be able to use a ruler for this. You just draw a line along from the reactants, which I'm just going to label as R, and you join it up with an arrow. It's quite difficult to do this with a laptop pad. So that's the activation energy. In a different colour, you could have also labelled the overall energy change, which is just the difference between the lines for the reactants and the products, which would be here. And if you ever want to easily label the change in thermal energy, it's just a little triangle and an E. So what I'd like you to do by this lesson is, like I said, if you're in top set, you're doing the higher questions. If you're in second or third set, you should be doing the foundation questions. I'd like to email your completed booklet along with the questions back to your class teacher. You need to complete your Educate quiz as well. And please bear in mind that these lessons do need to be done even though you are back in school. You need to be completing these lessons as usual. Any questions, please let your class teacher know.